Hello everybody. Let's do the notes for parametrically defined curves. So the big idea of parametrically defined functions is that we're going to describe movement along a path in the xy plane. And the way we're going to do it is using two separate equations. Each equation will tell you an x coordinate or a y coordinate when you plug in a particular time. So let's look at an example like we're in Algebra 1. We'll just plug in a bunch of times to these two equations, and we'll see what the x and the y coordinates are. We'll plot them, and then that'll show us the movement along the path. So let's make sure I know where these numbers are coming from so far. So when I plug in times 0 to the x equation, I get 0 minus 2 squared becomes 4 divided by 10. So that's where the 4/10 came from. If I plug time equals 0 into the y equation, I get 10 minus 0 is 10. So what that tells me is that at time 0, my x-coordinate is 4/10, which is about right here, and my y-coordinate is 10, which is way up here. So this point up here is where I start at time 0. Okay, I'm going to rapidly fill in the rest of the table. You should pause the video and do so yourself. Okay, so I've got all my coordinates. Let's start plotting them. We don't have to write the time at every single point. We'll just write it for the first and the last times. All right, so when you divide things by 10, remember you can think about that as moving the decimal place 1 over. So I have an x-coordinate of 1/10 and a y-coordinate of 9. Here I've got an x-coordinate of 0 and a y-coordinate of 8. Here I've got an x-coordinate of 1/10 and a y-coordinate of 7. Here I've got an x-coordinate of 4/10, 2/5, and a y-coordinate of 6. Here I've got 9/10, almost 1, and a y-coordinate of 5. Here I've got 1.6 and a y-coordinate of 4. Here I've got an x-coordinate of 2.5 and a y-coordinate of 3. Here I've got an x-coordinate of 3.6 and a y-coordinate of 2. X-coordinate of almost 5, 4.9, and a y-coordinate of 1. And finally, an x-coordinate of 6.4 and a y-coordinate of 0. And that's time equals 10. Okay, so if I'm starting at time 0 and I'm proceeding this direction, what you usually do to show the path is you connect all the points with a line, but then you also add little arrows that show the direction of motion as time increases. So this would be a perfectly great graph of this pair of parametric functions. Okay, what about this pair of functions? I've got an x-coordinate given by 10 minus t and a y-coordinate given by t squared. Rather than making a whole table of values, here I've plotted the graphs with a t-axis and an x-axis and a t-axis and a y-axis. So if I think about just the change in y value as time increases, my y value I know is going to be going up at an accelerated pace. Okay, so I'm imagining going up at an accelerating pace. So as I'm doing that, what's happening with the x values? So at time equals 0, the x value starts at 10. So actually I'm starting over here at time 0. And as time increases, my x value is slowly decreasing at a constant rate. So at time 0, it's 10. At time 5, my x-coordinate's 5. At time 10, my x-coordinate's 0. So now let's imagine putting those two things together. My y-coordinate is going to increase accelerating at the same time that my x-coordinate goes to the left. Uh-oh, the lights have gone off. And they're back. So for some simple shapes, you don't need to plot a bunch of points. You can almost imagine it. Just to be safe, let's plot a couple of points. Let's just plot at t equals 0, 5, and 10. So at t equals 0, I've got an x-coordinate of 10 and a y-coordinate of 0. At t equals 5, I've got an x-coordinate of 5 and a y-coordinate of 25. At t equals 10, my x-coordinate is at 0, and my y-coordinate is at 100 up here. And so if I imagine connecting them, this is what I get. hopefully this makes sense. You can see that the y-coordinate has this increasing accelerated rate of increase, so it's this kind of parabolic shape. But instead of being in a parabola this direction, it's a parabola in the other direction because the x values start at 10 and decrease. So I'm starting at 10 and decreasing. All right, last thing. Sometimes it would be nice if you have two parametrically defined equations to try and figure out what's the regular old y in terms of x equation. That's what the word Cartesian equation means. Cartesian equation just means an equation that relates x and y directly. So the way you can do this is just like solving a system. Here I have two equations and they both have t. What if I tried to substitute so that I just had one equation without any t? Let's go ahead and write the two equations. So I've got x equals 10 minus t, y equals t squared. What I'm going to do is I'm going to isolate t. So I could add t to both sides. And then I'll subtract x from both sides to get t equals 10 minus x. OK, so I've isolated t. Now that I know what t is, I can plug that into the t value in this other equation. So rather than saying y equals t squared, I know that t is actually 10 minus x. So I get y equals 10 minus x squared. And that's my Cartesian equation. Hopefully, it makes sense that this equation matches the graph that we have over here. At the very least, you can see that if we plugged in an x value of 10, we would have 10 minus 10 is 0, squared is 0. And that corresponds to the vertex located here at x equals 10. OK, most of the thinking is in the problem set. I think that's all I want to tell you right now. Good luck.